Bismillah ar-Rahman rahim. Dear students, today in a computer graphics, we talk about what's called as the hidden surface removal, okay, or we sometimes call it as visible surface detection. Basically, what is this all about is you want to have a 3D object, okay. Say for example, you got this 3D object, and you have to, uh, you know, transform it, and you have to plot it onto the plane, because when you want to put it onto the screen, and screen we know is a 2D, and you have to put this onto the 2D surface. Now when you do it on a 2D plane, right, so that means there are many lines, as you could see, or surfaces. There are lines in this case, and even the surfaces which cannot be seen if you see it from this side. For example, if my eye is here and I want to see it, so definitely those lines, for example, say let me color it up. Let me color it up red. So if I color it up, I'm seeing it, say for example like this. So if you see those back lines, or the back faces, they will go off, right? This is, say for example, the front row, and now I could see, if I'm seeing from the front, okay, and I could see only this much. So this side is gone, the back side is gone, okay, and the bottom side is all the time gone, and only I can see this surface and this surface. So that means when I want to convert this 3D object onto the 2D screen, I should not waste my CPU cycles on drawing those surfaces which are not visible, which is not going to be visible to the user, uh, to the seer, the viewer who is viewing it from some angle. So it depends on the angle actually, which surface is going to be visible. Say for example, we are viewing uh, from the z. If, say for example, this is my x and this is my y, and I am seeing through the positive z and towards this way, or some line, some angle parallel to the z axis, and I am watching it from that. So this is my assumption, that I am watching through the z axis, okay. And second, the polygons, the most often we talk here is the polygons are opaque. If they are transparent, then we can see the back lines, right? But we say they are opaque. So the assumption one is that we are watching through the z-axis, and second is that we got opaque. Now if we see, we have already done the clipping, right? We have done the clipping, but the clipping what we have done is actually, uh, this is what's called as an outside. You know, you are clipping something which is outside your viewing frustum. So view frustum clipping is you remove something. You know, this is your window, and something was, say there was a tree here, there was a car here. Now these are not visible, and say you have got a person here, and say you got this much, so you can see only what is visible in a window. So rest you clip, so that's called a clipping, that you are hiding what's not visible in your view frustum, okay. So you are removing polygons outside the view volume, okay, by doing 3D clipping, or Lang-Burske 3D clipping, or whatever you clipping you use, that you want to clip that part which is outside the viewing volume. You just clip it, cut it, and you keep only that thing which is coming in your frame, right? But the uh, now hidden surface removals, what we are doing is we are basically talking about inside the object, which is which we can see on the polygon, or if we talk more particularly on the polygons which can be seen in this frame, okay. Now in these polygons we may have the faces which are the back faces which are not visible, so we need to remove them. So that's what we call the back face removal or elimination, or back face culling. Or alternative, we can see what is visible. Okay, the visible surface or visible faces detection. We detect the visible faces, or we hide the back faces which are not going to be visible. Okay, and why we going to remove them? Because they are going to take the unnecessary, they're expensive operations. It takes up the CPU time, and we should be doing them because they won't be we won't be able to see them when we plot this 3D object onto the 2D 2D the screen. Like in this pic, there are no lines removed. Okay, it's a wireframe and we see the back lines are there, back surfaces are there, so we're not going to remove them. And here I am seeing those back lines which were there, they are just simply removed. Okay, so that will save a lot of CPU time, because we don't have to actually draw those lines. The CPU does not have to draw those lines, right? Okay, so these lines, the back lines, a lot of lines there which need not to be drawn. Say for example, there's also the line which is here, no, this thickness which is also there. And there are also surfaces. Now I am removing totally the whole surface, not only the lines but the back, that this back surface. Okay, the surface there, that's being removed totally here. Okay, so you can remove the surfaces also. Then there is occlusion also. There's a full occlusion. For there is a rectangle and a triangle. The triangle is totally behind this rectangle, which is not visible. It's partially this is partial occlusion, and this is none. There is no occlusion here. There is a full occlusion. So depending on that, what you want to show and what you do not want to show is important. So if the triangle is totally behind this rectangle, and this rectangle is opaque, so we don't have to at all draw the triangle, right? So we will not waste our time drawing the triangle, because that will not be visible on the screen. Now for this we have actually two types of methods for doing the backs hidden surface removal or hidden lines removal. We got two algorithms for that, right? The first one is once again, the first one we have is object space. We call them as the object space methods, which work on the object space. And number second is actually what's called as an image space. So there are two uh, grossly two methods for doing the visible surface detection or hidden surface removal. So what is the object space which works on the actual object? Okay, it is based on the object. It concentrates basically on the geometrical relationships among objects. It compares the objects together and then figures out how to remove the hidden lines and all. But in image space, it's actually after projection. You have done the projection of the object. Okay, you have done the projection of 3D object on the 2D screen. Now it is all dealing with the pixels. Okay, so you are taking single pixel into consideration and then determine which surfaces or which lines you do not want to show or you want to hide. Okay, so it will depend upon the resolution, but here it does not depend on resolution, right? Because it depends on the geometrical relationships among the objects. One object is hiding the other object, the triangle is coming behind the rectangle and all. You compare these objects together and see what are their positions and how which lines are actually hiding and all that. So here you talk about the surfaces or lines, but here you talk about the pixels, the points. Okay, you talk about the points, and here we talk about the these were designed for the vector graphics. Okay, and these are designed for the raster graphics, where we talk about the pixels and resolutions and all that, right? And we have the two algorithms to read about here. One is your in the object space, uh, that's the back face removal algorithm or method, and we got here the z buffer technique or method in the image space, which we will discuss later. Okay, so this is my object space method and image space method. It deals with the object definition directly, compares the object with each other, and then determines which surface is visible. And in image space method, it deals with the projected image, the 3D on the 2D screen we have projected. So we got to talk about the visibility in terms of pixel position and the projection on the projection plane on which it is being projected, on the screen is projected. Okay, and most visible surface algorithms actually use the image space methods. And the first method we have is called the back face detection. Okay, method. It's a simplest kind of thing. It's common to actually all methods we'll read about. Okay, where we remove the hidden surface from the 3D objects by the plane equation methods, and it uses the inside outside test. We talk about it now. One more thing we need to know about this object space is they are computation intensive. That is the drawback of it. Maybe the cons of it. It's a competition. It is competition intensive. It will take a lot of CPU intensive. It takes a lot of CPU time. Okay, uh, and it depends on the scene's complexity. uh, and this guy is a little simple. Okay, it's based on the pixel based, and it's not that intensive in computation than your object space methods. Okay, but there is also the advantage in this is that we do not require here the device. It doesn't depend on the devices, but it does depend on the image space is on depends on the projection plane on which it is being projected. So it depends on the devices, its resolution and all that thing. But here it is independent of resolution and independent of any device, but it does depend on the scene, the complexity of the scene. The scene is complex, it may become totally infeasible. So uh, therefore if you want to apply these object space methods, it has to be done on a very simple scenes, right? Not on a complex scenes at all. But here you can use this on a complex scenes, and that's why maximum algorithms which use the no visible surface detection or hidden surface removal techniques, they use the image space method. Now let us talk about the back face removal method or technique. Okay, it's also sometimes called back face culling. We also called it sometimes back face culling method, or we can say it a back face elimination, sometimes also called as back face elimination method, right? And it's a simplest. The first thing is it's a simplest method, and it helps to remove a lot of hidden faces uh, from the polygons, right? If we have a polygons and we want to remove the hidden surfaces, this is really going to help us. So what is our objective here? If we talk about what's the objective, it is going to firstly detect the back faces of the objects, or more technically polygons, back faces of polygons. Firstly detect the back polygons and then remove them. This is our objective. Now this is actually a two-step process. We have here two steps. Number one is we need to know whether the point we are talking about, for example we talk about just a single point, is it inside that object or not. So for example I'm talking about this object, okay, and I want to remove the back faces, and I'm talking about some point. Say for this is my point. I'm talking about this point, and say my screen is this much, okay, and my object is here, and I'm talking about this point, or I may talk about this point. Okay, now the first thing is The point I am talking about is the point, I could say, is the point under consideration inside object. Is it inside or outside object? If it's outside object, then I don't need to care about if I'm talking about. So firstly is the point I'm talking about, then I will see the whole line and whole surface. But we start from the point. Is that point under consideration inside object? And sub number second comes then, if I found it, hey bro, it's inside the object, then I should do the second step, that is to see whether it is visible or not. That means if I view it, say for example my viewing angle is, this is my eye, okay, which is viewing from this direction, is it viewable or is it on the hidden surface? Or in other words, we could say, is it on a visible surface or is it on a hidden surface? Say for example this point is on this surface, which is on the back side, which may not be visible. So I need to figure it out, that whether this point is the point, is the above point, okay, visible or hidden. So how I figure out these two things? Is the point under consideration inside the object? And if it is inside the object, only then if it is visible or it is on a hidden surface, right? If I see this is actually on the hidden surface, then I do not need to care about it, because I'm not going to draw it, right? Anyways, so I should ignore it. But if it is on a visible surface, then I need to draw it, right? Now, how you figure out the point number one is by the inside outside test. So we do inside outside test on that point. So how we do the inside outside test? So we are doing inside outside test. But how we do this inside outside test? To figure it out, that whether that point is inside my surface or my object, or it's outside my object. So for that we use a, there's a very famous surface equation. If we have, for example, a surface, any surface, okay, with its coordinates x, y, and z. Say for example, if I talk about this surface with its x, y, and z coordinates, okay, and with the surface parameters on any surface, they have its parameters like a, b, c, and d, okay. You can see more about it, learn more about it, the surface equation, if you want to, from the internet. So every surface has its coordinates, x, y, z coordinates, and a, b, c, d as their parameters. So we have the surface parameters a, b, c, d, and surface coordinates, and we know surface x, y, z, and we have an equation that a times x plus b times y plus c times z plus d, if this is coming less than 0, okay, if we calculate on this surface with these surface parameters and its coordinates, that a times x plus b times y plus c times z plus d, if it is less than 0, then we say that point, if we talk about any point with the coordinates x, y, z, okay, I'm talking about this point with its coordinates, what is its x, what is its y, and what is its z coordinates, because this is a 3D point, right? So we need to talk about the x, y, and z coordinates of that point, and with the surface parameters of a, b, c, d, I multiply that with the surface parameters, and if it's coming less than 0, then it's gonna be on that object. So this is simple as this. So I can figure out the first point I need to know is whether this point I'm talking about is on the object or not, or it's outside object. So we say inside outside test. If it's coming less than 0, it is inside object. If it's coming greater than 0, it is going to be outside the object. Simple as it is. Okay. Okay, now the next point is how to see whether that is on a hidden surface or it is on the back face. Is it on a back face or a hidden face, or is it on a visible face, right? Say for example this is my eye which is watching it, so which is making some angle, say L, say this is the L, the vector, which is on this surface, and every surface has a normal. You should know that every surface is a normal is 90 degree. Okay, so every surface has a normal. Say for instance, this is a normal like this, so we call it n, and this point is making an angle theta with this L and N. L is the viewing vector and N is the normal. Okay, is a normal vector. Okay, so I want to figure it out that whether this point is visible or not. For that, I need to do the dot product of L dot N. Okay, uh, maybe I call it L or I call it V. Some books write it V. That's the viewing vector. Or some books write it L. So you'd say you can do the L dot N. Okay, and if it is coming greater than 0, so we say that it is on the back face. If it is not greater than 0, if it's less than or equal to 0, then it is gonna be on a visible face. So this is how we detect the visible surfaces or the back faces here. So if this point is coming, or this surface, then totally, all that surface, then with all those points, and with L dot N, if I do the dot product of L is the viewing vector and theta is the N is the normal on that surface, then if I multiply the dot product of them is coming greater than 0, then we say that this is on a hidden surface. So by that, if it is greater than 0, we detect the back face. This is how we do detect the back face of that object, right? But now how to do this actual dot product? Let's learn about this now. If you look at this, this is the 6 faces of a cube. Okay, and the normal vectors, we have the normal vectors here, as you could see here. This is normal vector, this is the normal vector, this is the normal vector of this surface, this normal. So because if I'm talking of this point which is on a back face, right, then I need to calculate this theta, the angle between the L is, this is your eye, it's actually the eye not properly visible. This is the eye, where because the which surface is hidden or which surface is visible depends upon your this L vector, that is the viewing vector, right? uh, because you may see from there, you may see from this side, you may see from this side. So I told you the assumption is we see it from the z-axis, okay, and calculate the rest. uh, so the vector n1 n2 or the normal to the surface is 1, so surface 1 and surface 2, they are normal to that, and L points from surface 1 to the viewpoint. Now L is something which points from surface 1, so this is the surface 1 here, as you would see, this is surface 2, okay, and the L is on a surface 1. So this L points from surface 1 on to the viewing viewpoint or your eye. So simply the surface 1 is visible to the viewer while the surface 2 cannot be visible because it is hidden, but we need to calculate that whether how to do this, right? Let me go to the next slide. So this is what I am saying, that if the theta which is coming, because I told you if this is my okay cube here, let me draw it then like this, like this, like this, and like this, and if you have the L, okay, and this is the normal N, okay, this is L and this is N, and this is the theta, the angle between the two, okay, and we usually take them as a unit vector. You should also know that their length is 1, we take as a unit vector. This L is as a 1 unit vector and N also as a unit vector, okay, and the theta is the angle and this theta need to be between 0 to 90 degree, or in other words we can write it that 0 is less than equal to cos theta is less than equal to 1. We can write it like this way or we can write it this way, right? Okay, now what we're talking about is that we need to determine the visibility, and I'm saying that I have the L, that is the viewing vector, and N is the normal, and their Cartesian coordinates are xyz from both of these. So L is actually the three components: L of x, L of y, and L of z. And n is n of x, n of y, and n of z. That's why we say L is a vector and n is a vector. It's not a scalar, it's vector. Okay. And then if you want basically to calculate L dot n, because I told you that if L dot n is greater than 0, then it is hidden, right? But the question is how I calculate L dot n, how I do the vector multiplication of L and n. Okay. I just make it again. What is L and what is n? Don't actually confuse with that. So if I'm the point is emanating from here, let me change the color to the black. Okay, if the point is emanating here, this is your I is here, so then it will be called L, which is with the viewing vector. And if it is the normal to that surface, okay, 90 degree to that surface, that's a normal, then that's n. And we know L is a vector because it has three components, that is L of x, L of y, and L of z. And n is also a vector which has three components, n of x, n of y, and n of z. So my answer to the question that whether this point is on a back face or a front face, is it visible or is it hidden, is done by multiplication of L to the n. So we see at that point what is the viewing vector and what is the normal, and we want to do the dot product of L of n, and if it is greater than 0, then I say it's hidden. But the question is how I do that. I do that by the vector multiplication of, we calculate this theta, and we say absolute of L and absolute of n into cos theta. This is how we calculate the no dot product of L dot n. So if you have a two uh, vectors to multiply, basically you do absolute of n and absolute of L and cos theta. This is the well known in the mathematics. Now we can shorten this up, because I said L, sorry, let me take a pen. I said L dot n is equal to actually absolute of L, absolute of n, and cos theta. But we have, since we have these unit vectors, they are all one. So L is 1, n is 1. So these are unit vectors, they cancel out. So L dot n is actually equal to cos theta. Okay? Because they are unit vectors of length 1. So if you have to say L dot n, basically it is having three components. Basically you are multiplying L, which is actually L of x dot L of y and dot L of z. These are three components, and n is also three components: n of x, n of y, and n of z, right? So n is three components, L is three components. Okay, and you are actually doing the dot product, so you are multiplying L of x with the n of x. So L of x, n of x, L of y with the n of y, L of y, n of y, L of z with the n of z, and that is this thing, right? And since we are viewing from the z-axis, right? So because I told you that our assumption is to view from the z-axis, our viewing uh, uh, axis is the z, right? So what does that mean? So what that technically means is that because we are watching from the z-axis, so that means if I say L, because I say L is actually made up of L of x, L of y, and L of z, right? So actually this is 0 0 L of z, because L of x, L of y, it doesn't matter. L of z, because we are watching from the z-axis, so these x and y component become 0, and it's only L of z. And same is n. N is also made up of n of x, n of y, and n of z. So that also these two components become 0 on a normal, because we are seeing from the z-axis, and this becomes n of z. So in totality it is a 0 0 L of z multiplied by 0 0 n of z, right? Okay, so 0 0 0 gone, so in totality if we multiply it, it becomes 0 into 0 0 into 0 L of z into n of z. So this is L of z into n of z in totality. So this whole thing comes, L dot n actually comes about L of z dot n of z, and L of z is the viewing vector, we already know. So we all only need to calculate n of z. So simplified version is to find L dot n, we need to only, because why we are doing L dot n, because if L dot n comes greater than 0, it's a back phase. So here we need to calculate only n of z. Okay, and we see the sign of n of z. If this sign of n of z is greater than 0, okay, then it's gonna be the back face, or if it is less than 0, it is gonna be the front face. Let me repeat, because I said if L dot n is greater than 0, it's going to be back face. Now it depends upon n of z, because L of z is always constant here, because we see from the z axis, and n of z actually decides whether this is going to be back face, whether this is going to be positive or not. So it has to be greater than or equal to 0. If it is greater than or equal to 0, this L into n will be positive. That means then it is back face. But if n of z is less than 0, okay, if n of z, let me write it a little here, if n of z is greater than 0, it is back face, equal to 0, and if n of z is less than 0, it is going to be the front face. Okay, so I don't need to hide it, right? So this whole equation actually depends upon the n of z now. So that means if n of z is greater than 0, it's going to be the it's going to be backface, because overall the whole value L of L dot n comes to be equal to greater than 0. And if n of z is less than 0, so this will come negative, so that means it is a front face. So if we are saying in a simpler sense, that if my object and is on the negative axis of z axis, okay, on the negative side of the z axis, because you are weaving from the z axis, and if your the point is on the negative side of the z axis, okay, because uh, at all we need to calculate only n of z, okay, because x and y's, they remain constant, so they are zeros. So this will be L dot n actually will be equal to L of z into n of z, and L of z is a constant here. N of z, if that is coming normal, is that's coming on the negative side of the z axis, it's gonna be the basically uh, that means n of z will come actually greater than or equal to 0. So that means this is going to be on a back face. So the sign of n of z in this multiplication tell us whether the point is on a back face or it is on a front face. So this is our algorithm for the back face removal algorithm, and that too for the all the polygons. If we have many polygons in a scene, okay, for all the polygons, what we do is we do the numbering of polygons in a clockwise direction. We move from the clockwise direction, see all the polygons, say this is polygon 1, this is polygon 2, this is polygon 3, and so on. We number them 1 2 3 and so on, okay, using call it v1 v2 v3. Then we calculate the normal vectors, that is n1, okay, that will be equal to v2 minus v1 into v3 minus v2 and so on. And then consider the projector L. Some books write it L, some write it P, some write it V. So whatever you write to call it V or P or whatever, the projectile you say P, or weaving angle say V or L. That's the projection from any vertex. Then you need to calculate the dot product of this L and N. I told you how to do that. And basically it is actually the modulus of L and modulus of N into the cos theta. Then because L is a vector which is actually made of L of x, L of y, and L of z, and N is also the vector that's actually made of N of x, N of y, and N of z. And since we are moving from the z axis, so they will come out to 0, they will come out to 0. The multiplication will be actually L of x into N of L of z into N of z, okay, and it is actually the sign of n of z which will tell us whether the dot is greater than equal to 0 or not, right? So you don't need to do the cos theta, you don't need to do anything, you need to only see the n of z, okay. If n of z is greater than 0, if it is making this dot greater than equal to 0, then surface is visible, or else it's not visible, simple as it is. And that's it. So that's all for the backface removal algorithm, and which was the object space method. Now we say image space method, and in that we have the z buffer that we will see next time. So then, see you next time. Until then, masalama.